All right, let's correct some things right off the bat. First of all, you didn't record a shadow. You recorded something called a silhouette. There's a difference. Secondly, what I recorded was not a shadow, was a silhouette. You did not do parallax measurements. I did, which means I have the capability of figuring out how far away from us it was, and by knowing my angle at which I observed it, I can figure out its altitude. You did not take these measurements. So you cannot make any claims as to how far away it is, how high it is, how fast it's going, anything. The only thing you can say for certain is that I saw something. Well, that's great. That doesn't confirm what you say it is, which is, quote, a balloon satellite, which, by the way, there's no such thing.
An inflatable plastic balloon satellite, 100 feet in diameter, tall as a 10-story building, will be sent aloft folded accordion fashion inside a 26.5-inch magnesium container. The latter is mounted in the nose of a 3-stage 92-foot Thor Delta rocket. Highlighting one of the nation's proudest days in space, the satellite, called Echo 1, will serve as a reflector for radio waves that bounce back to Earth, paving the way for a new kind of worldwide communications. The rocket at Cape Canaveral carries the balloon and 30 pounds of powder, which will turn to gas and inflate it at a height above 1,000 miles. At 5:40 a.m., the launching. Then the tense moments while the rocket goes through the separation of the stages. It is only the second launching for the Thor Delta, and as shown in this animated visualization, it is living up to the expectations of the space experts who say it functions almost perfectly. With extremely precise guidance, it is placing the balloon satellite almost exactly into the desired 1,000-mile-high circular orbit. "33 minutes after launching, the balloon is released and inflated by the powder inside, which turns from a solid into gas under the sun's temperature. The big balloon, visible like a bright star, quickly bounces a recorded message by President Eisenhower between stations in California and New Jersey. And here in Washington, the chief executive listens to his own voice as it sounded when bounced from the orbiting satellite.
It is a great personal satisfaction to participate in this first experiment in communications, involving the use of the satellite balloon known as Echo. This is one more significant step in the United States program of space research and exploration.
Which is, quote, a balloon satellite, which, by the way, there's no such thing.
While many of us take the internet for granted, large parts of the world are still unconnected. In big towns and cities, providing connectivity with cell towers is economical, as there are lots of people there wanting to connect. But the further away from these towns and cities you go, the fewer people there are, until eventually connectivity just stops. To bring the internet to people in these areas, we need to look up, way up, into the stratosphere. From here, we can provide connectivity across much larger areas, bringing the benefits of the internet to more people. So how do we get there? With balloons. Really big balloons. Beginning their journey from one of our custom-built balloon launchers, our balloons are filled with lighter-than-air gas and released up into the skies. Rising 20 kilometers into the stratosphere, loon balloons float twice as high as airplanes, well above weather and wildlife. To get to where they need to go, loon balloons sail the winds by moving up or down into different wind currents traveling in different directions, joining other balloons in small teams over areas where connectivity is needed. Ground stations connected to local internet service providers send signal up to the balloons and then back down to the ground over large distances, allowing people to connect directly to the internet with an LTE mobile phone. When it is eventually time for our balloons to come down, we navigate them to remote areas and work with local air traffic control to manage their slow descent down to Earth, where they're collected by our recovery teams. By repeating this process at scale, we hope to provide continued connectivity to users on the ground, bringing the internet to more people in more places around the world.
A balloon satellite, which, by the way, there's no such thing.
It's the coldest, driest, highest, and windiest continent on Earth. Despite its reputation for the fiercest weather on the planet, Antarctica is a hotspot for scientific ballooning. The reason is Antarctica's circumpolar winds.
Cool. Oh. That was awesome. That was awesome.
These high stratospheric level winds set up during the Antarctic summer and circulate around the South Pole in a counterclockwise direction. This means NASA's giant scientific balloons, the largest being nearly 40 million cubic feet, can be launched, ascend to 120,000 plus feet, the edge of space, and sail the circumpolar wind around the continent for 10 to 20 days on average. And in some of the most successful instances, flights can be terminated and the balloon and payload recovered. All within 100 miles of where they were launched. Riding this Antarctic vortex in 2008, a 7 million cubic foot super pressure test balloon flew for 54 days, setting a stratospheric scientific balloon flight duration record. Scientific ballooning operations here on the ice are the result of a unique partnership between the National Science Foundation and the NASA Balloon Program. NASA funds the science, and NSF provides the support to scientific teams and their balloon-borne experiments. Like this one called STO, or the Stratospheric Terahertz Observatory. It's being readied for its first Antarctic summer flight at the NASA NSF Long Duration Balloon Facility at Williams Field. The LDB launch facility is located on the Ross Ice Shelf, a 45-minute drive from McMurdo Station, when the weather's favorable. STO is designed to address a key problem in modern astrophysics, which is understanding the life cycle of star-forming molecular clouds in our Milky Way galaxy.
What we're doing is looking at specific emission features from carbon and nitrogen atoms out in space within our own galaxy.
In doing so, STO will map a swath of our galaxy with the world's most sensitive high-frequency radio receivers, essentially listening in to how clouds of gas and dust, which permeate the Milky Way, coalesce to ultimately spawn stars and planets.
But for instance, no one's actually ever captured a cloud, one of these molecular clouds in the process of formation. No one's been able to see that.
One reason is these atoms and molecules radiate at such a high frequency, over 1,000 billion cycles per second. Too slow to be observed with the human eye, but too fast to be observed through the blanket of water vapor that envelops the Earth's surface. With STO, primary investigator Chris Walker and his multinational team have developed a way to capture and focus this far infrared light using a conventional optical telescope on a high-altitude balloon platform that flies far above most of the Earth's obscuring water vapor.
The light comes in, hits this mirror, goes up to a secondary mirror, and then sends it back through a hole in the bottom of the telescope. It comes right out the bottom of that telescope.
From there, a secondary optic system channels the far infrared light to superconducting detectors held within 5 Kelvin of absolute zero inside a liquid helium-cooled dewar. The telescope and the dewar, Walker is proud to point out, are recycled components.
And the original telescope was built, the way I understand the history, for flying on the space shuttle, but it never flew. And so it was actually in a warehouse at the Smithsonian, I was told.
and the cryostat was a prototype to cool instruments for the Spitzer Space Telescope.
We put the two together and we really have a space-grade instrument that we're flying on the balloon.
Walker is equally savvy about how the economics of scientific ballooning can help further his team's science.
Well, it's a huge significant stride forward. The main reason is when you compare balloon flights to space flights, you're limited in the size of your payload and the amount of power it can take. You're usually limited to an instrument that weighs a couple hundred pounds and takes a couple hundred watts. But with the balloon, you can actually fly much larger instruments that can look at a whole bunch of more of the Milky Way or extragalactic space than you would normally. In the end, you can do more science than you could from orbit at a much smaller price.
STO was successfully readied and launched on January 15, 2012. Carried aloft by a conventional 39 million cubic foot zero-pressure balloon, the STO flight lasted for 14 days, completely circumnavigating Antarctica. The mission allowed extensive testing of many flight systems to be conducted. STO was successfully terminated, recovered, and reconfigured to fly again in Antarctica on December 9, 2016. The STO-2 flight lasted for 20 days, circumnavigating the continent twice. The mission verified the operational capability of advanced flight systems critical to the next generation of terahertz balloon-borne observatories, GUSTO.
Which is, quote, a balloon satellite, which, by the way, there's no such thing.
GUSTO will map the interstellar medium between 4 and 8 times faster than STO-2 and do so for 5 times longer, allowing a significant fraction of the Milky Way and all of the Large Magellanic Cloud to be surveyed in a single flight. It's an example of a new class of sophisticated science payload designed to take advantage of the revolutionary capabilities of NASA's new super pressure balloon platform, designed and engineered to keep science payloads aloft for 100+ days.
So the cutting edge of science is independent of the tool you're using to advance the science. There are still compelling science questions which can be answered on balloon platforms, and since balloon platforms are the most cost-effective way of going after these really important science questions, that's the way we should do it.
What the new scientific ballooning capabilities are offering us is a technology. It's an enabling technology to get us to the edge of space, scientifically meaningful, for a longer duration at a reasonable cost. That's the technology. The need is there's lots of great science to be done that we can do on these platforms at lower cost and get the important training to be able to test out instruments. You know, we may test out things that are very high value on a scientific balloon in anticipation of a future flight opportunity. And so now we've met a need with the technology, and that's real innovation. You know, that's when NASA makes progress.
realize this, but the majority of the world is not connected to the internet. How do we get cost-effective, inexpensive, and reliable connectivity to the remaining 5 or 6 billion people in the world who don't have it?
Yeah, we could be up in an hour.
Project Loon is the idea that we could create a network of high-altitude balloons that float about 20 kilometers up, and through this network we can give the internet to the entire world. Our balloons are these great big round things, about 15 meters in diameter, but you'd have to have a telescope if you wanted to see one up in the sky. So here's the surface of the planet. From here, right up to about 10 kilometers, this is where rain happens, this is where mountains are, and pretty much all aircraft fly down here. Now, here's our little balloon up here. This is right around 20 kilometers, actually in the stratosphere. And the stratosphere is different because we tend to have layers of wind that go in very particular directions. And by moving up and down through these different layers, we can steer. So by catching the right wind, we can keep the balloons together enough to give good coverage on the ground.
We can sail with the winds and shape the waves and patterns of these balloons so that when one balloon leaves, another balloon is set to take its place.
The balloons communicate with specialized internet antennas on the ground. So this antenna here points up at the sky and talks to this balloon. And each one of these balloons talks to their neighboring balloons, and then back down to the ground station, which is connected to the local internet provider. What this does is it creates a network in the sky.
Let's carry on then. We need to get that antenna off.
We've designed our radios and antennas specifically to receive signals from Project Loon only in order to achieve the high bandwidth over long distances involved. If we didn't filter out the other signals, the technology just wouldn't work.
I got it. Actually, this will probably...
The balloons are completely solar powered, and we control them through Loon Mission Control.
All right, I think your plan is great. Do the ascent on 46 and 47. Try it like an hour after float.
Yeah. Okay, we're going to be off the ground in a couple minutes.
Before we send them up, we talk to air traffic control. We let them know these balloons are on the way up so they know where they are. And before they come down, we also talk to air traffic control.
Okay, and they're on a different one now.
We can direct them to land in various collection points around the world in order to reuse and recycle their parts. Now, we have some ability to steer in general. However, in the stratosphere, most of the time, the winds actually flow from west to east. Because the winds generally circulate this way, we typically will have bands of our balloons that will be around the world at different latitudes.
So if the balloons are circling around the bottom half of the world, eventually the balloon that's over South Africa will pass over South America.
1, 2, 3.
Woo! We're using the sunlight, we're using the wind, we're using all of these things to build this network in the sky.
Project Loon is working to bring the technologies of access to everyone on the planet.
So our goal for these balloon flights is to stay aloft for 100 days or 3 laps around the globe. 100 days is long enough to get a good life out of it, but not so long that we have outmoded technology in the air. The most important part about keeping balloons in the air for a long time is making sure that they are leak-proof. That's a very difficult challenge. The surface area of the balloon is really vast, about 500 square meters, and it provides a lot of opportunities for little pinholes and leaks, which can shorten the life of our flight. Every morning when the sun comes up, our balloon gets warmer, and we stress it all day long with altitude control maneuvers, pumping air in and out, changing our internal pressure. And at night, our balloon gets very, very cold, and it becomes contracted and brittle. Our balloon material is like a rubber band. When you stretch it over and over and over, you eventually will break it. When you put it in a freezer and stretch it too far just once, it will snap. So engineering the right material is very important. Today, I'm preparing some samples for our engineers to test. We do a lot of testing, biaxial strain, instron pull tests at cold under UV degradation, figuring out how to make the material more durable. We also do full-scale tests to find leaks, inflating the balloon to a full pressure with helium and sniffing the helium with a special sensor all the way around the outside to try and detect a leak. Project Balloon is part of a very long tradition of balloon science. Having a balloon stay up for so long helps us contribute to the legacy of ballooning.
The altitude that we fly at is actually above 99% of the atmosphere, which means that we have a lot of the same physical challenges as flying in outer space, and yet we still have to deal with the chaotic nature of the wind patterns. We need to know what the winds are in the stratosphere so we can surf those winds in order to go different places. We've been using some wonderful data we have from the National Oceanic and Atmospheric Administration, which gives us their best predictions of which directions the winds are blowing up in the stratosphere. They get their data from things like weather balloons, but as a weather balloon goes up, it gets larger and larger until eventually it pops. So the amount of time it spends in the stratosphere is pretty limited. In comparison, we'll have a fleet of balloons that are in the air all the time. And of course we have GPS so we can see which ways the wind is blowing us. So we'll have a very rich stream of data coming into our system. You can kind of imagine putting a whole bunch of rubber ducks on a lake or an ocean and watch where they float to. You'd get a very good idea of what the water currents are doing, whereas our balloons would show you what the air currents are doing. So this simulation shows how we use the wind data to predict a balloon's trajectory. In this video, the red dot in the center is the balloon, and the arrows around it are the predicted wind field. So you can see as the wind field changes, the red arrow shows the velocity of the balloon as it travels through this ever-changing wind field. One question you might have is, are our balloons actually flying at the same speed as the wind? And it turns out that we can tell that they are because we've actually flown microphones on our balloons, and it's very quiet when we're flying in the stratosphere. That tells us there's no wind rushing past, and that's because we're flying at the same speed as the wind around us. Right now we're only flying a few balloons, but we're already gathering a lot of really exciting data that's helping us understand the stratospheric winds better. And as we have better understanding, that's enabling us to fly more balloons with greater confidence and provide ourselves with even more data. And so we have this ever-improving understanding of the stratosphere. We've actually been talking to NOAA and working with them to feed some of the data from our balloons back into their models. And as our fleet comes fully online, we'll be able to significantly improve the quality of the wind predictions that NOAA is able to provide to others as well.
We depend on communication satellites all the time. These space-based relay stations that receive, filter, and amplify signals from the ground before delivering them back to a specified point on Earth. But the first communication satellites were called ECHO, and they were passive communication satellites. The ECHO program began in 1956 as a National Advisory Committee for Aeronautics experiment. The idea was to use these large balloon-like satellites to test the effects of the upper atmosphere on lightweight bodies. Using them as a communications testbed was a secondary application dreamed up by two researchers with AT&T's Bell Telephone Laboratories. They realized that the giant reflective spheres were a great body off which to bounce signals, sending them from one earthly destination to another. ECHO 1 launched on August 12th of 1960 and saw a host of communications firsts. It enabled the first live satellite-based voice communication, which was a radio message delivered by President Eisenhower, the first satellite-transferred image, which was an image of the president, and the first transcontinental satellite phone call, which was made between two researchers. ECHO 2 followed on January 25th, 1964. It was a larger but similar satellite.
balloon to provide real continuous coverage. We're just transferring the signal from one balloon to the next as they pass over a stationary recipient. And so by having this continuous flow, we're always filling in the area that we need to provide the service to. And the biggest hurdle for a balloon is the wind. Once you've inflated the balloon, it gets quite large on the ground and acts as a large sail. It would catch the wind, and it was really hard to control it. So then you try to find locations around the world that had zero wind. But then you're limited in scope because you can't find these perfectly wind-free zones that provide access to the location where you want to provide internet coverage. And then for a given launch site, the ideal wind conditions would only exist for a very short period of the day, thus limiting the number of balloons we could get up in that period of time. We wanted to do something where we could launch one every 20 minutes. And so we needed to rethink how you would launch a balloon. We wanted to develop a launch system that would allow us to block the wind as much as possible, and it could launch balloons from a number of different remote locations and be nimble enough to deploy into a new area as we expanded the program.
We went into a very controlled environment and launched many balloons and measured all of the aspects of that launch. And then from there we developed our tooling in order to guide that motion. The auto launcher is 45 feet wide and 55 feet tall. The system is the 4-tired steerable gantry crane, and we outfitted it with hangar doors that allows it to become a wind block. It's a highly customized piece of equipment. There's nothing else like this in the world. We lift the balloon right out of the box, so we don't ever have to do any extra handling to the balloon. We have jib cranes to lift up the balloon at the top of the balloon to secure it while we're filling it. The wind does not bother the team because we have the ability to steer the crane, so we're always downwind. And when we're in the right wind pattern, we lift the entire perch up, and then we angle the perch, and then we launch the balloon. So where we had 16 people launching a balloon, we now can do it with 4 people, and we can do it in a very short period of time. We can now launch at will instead of at will of the weather, and we can launch in a consistent manner. So we can keep a continuous ring of balloons that circumnavigate the globe.
Which, by the way, there's no such thing.
My name is Nick Coley, and I'm a Flight Operations Program Manager on Project Loon. Our big goal is making sure that we return these experiments to our engineers back in the labs to study them, to be able to iterate off of them. The idea is that we fly this experiment and then we land this experiment, and unlike a lab where it's a controlled environment, our test tube is the world. As with any scientific experiment, measurement is a priority. We employ sensors on the balloons that constantly measure how the experiment is going. When we decide that it's time to end the experiment or to land a balloon for other reasons, we analyze wind patterns, we communicate with air traffic control and our team on the ground to work out where we're going to bring the balloon down safely. An ideal recovery spot would be a flat, unpopulated area that has good road access, but is also remote enough to not have obstructions or things that could create damage so if we landed in those areas. We have all of these location systems on our balloons. That makes recovery sometimes kind of like geocaching. We get a set of coordinates and we go to the set of coordinates and voila, there's a balloon.
There we go.
The better we get at long-term predictions and the better we get at navigating our balloons, the easier it's going to be to land our balloons in pre-selected recovery zones. That means it's going to be easier for our recovery teams to collect them and easier to bring the material back so we can recycle and reuse it.
Get a feel for what it looks like? Sure.
It's important for us to pick up after ourselves. we know that we can repurpose a lot of our electronics. So if we can take a simple component like a circuit board or a transponder and revalidate it after we bring it back to Mountain View and then use it 100 times over, that makes our system that much more economical for the future. It's better for the environment, and it's a lot better for our engineering team. Collecting the data from these experiments is so vital, it makes balloon recovery one of the most critical pieces of our operation.
Satellite, which, by the way, there's no such thing.
In rural areas, the infrastructure you would need for a terrestrial network is sometimes not economical. You would need to connect cell phone towers hundreds or thousands of kilometers over mountains or potentially crossing rivers and seas. Loon has decided to take a terrestrial infrastructure and sort of lift it up to the stratosphere, taking the most essential components, that is the antennas, and putting them on a balloon. In 2013, we did our first proof of concept test in New Zealand. A lot of the equipment was early prototype. It certainly was not a solution that you could scale up to millions of people. After the New Zealand experiment, we focused now on a scalable, deployable, worldwide solution. First, we needed a very reliable and robust high-throughput link to the existing internet. We beamed that signal up to the balloon through ground stations where the terrestrial internet network sort of ends and Loon starts, connecting the telcos up to the balloon. The balloon is not stationary, it's actually moving across the sky, so you need your antennas to be tracking that balloon continually and to be a high-throughput, reliable link. Once you get the data from the ground station up into the balloon, you need to connect multiple balloons in a chain in order to get the signal to where it needs to go. Sometimes hundreds or thousands of kilometers away from the ground station. So the balloon-to-balloon links are a really critical element of the Loon network. You can't string fiber between balloons, so the next best thing is to just beam the signal using lasers. You have these two free-floating platforms that are kind of swaying and bobbing freely. A dance, if you will, between the two balloons where the two lasers are trying to keep the beams locked onto each other as they drift in the sky. Everything has to be so precise and well-aligned to be able to provide reliable and robust connections. We've established gigabit per second connectivity between the balloons up in the stratosphere, hundreds of kilometers apart. Getting the signal down to the user. We're using LTE, so you could just use the same mobile devices used today to get service whenever there's a Loon balloon floating by. All of this technology coming together will ultimately allow someone who could be thousands of kilometers away from the nearest ground infrastructure to have access to the internet.
With a balloon, there's no need for rockets. To get a satellite to hover over the same spot on Earth, geostationary orbit, you have to be 36,000 kilometers away, too far to use some sensors, like radar. A balloon can sit 1,000 times closer, in the stratosphere, 30 to 40 kilometers above the Earth, and still be above 99% of the atmosphere with clear views of the stars or wide panoramas of Earth. You can bring down a balloon, tinker with onboard scientific equipment, and then launch again. Satellites, not so much. Cost is also a factor. NOAA's 4 new geostationary weather satellites are estimated to cost $11 billion, whereas a balloon flight might cost just a few $100,000. NASA's been flying balloons for a long time, but without any steering capabilities, they drift in the wind across continents. Now, private industry is getting in the balloon game, with new technologies that are enabling balloons to hover over one spot. These balloons rise and fall in the stratosphere, catching countervailing breezes that allow them to stay roughly in the same place. What can a balloon with a scientific payload do? It can look down at the Earth, checking on storms or animal migrations. It can look out into space, peering at the surface of the sun or collecting cosmic rays. It can even do things in the stratosphere, like studying how ice crystals could reflect sunlight and cool the planet. How do you keep a balloon stable enough to use a telescope? Gyroscopes can help keep a platform pointed at its target even as it sits in a twisting gondola.
was exciting while it lasted. Facebook and Google are both reportedly dropping some of their plans for satellite internet. Joining us now to discuss this is Michael Learmonth, technology editor at International Business Times. Michael, great to speak with you this morning.
Good to be here.
So, Facebook and Google, they've both had big ambitions for satellites in space, presumably to provide more internet access to more people. Why are we starting to see them scrap some of their plans now?
Well, this latest report comes from the Information. Facebook hasn't confirmed it yet, but it makes a ton of sense. I mean, satellites just aren't very good at delivering the internet. It's very expensive. The connection isn't very good. So there are just a lot of lower tech, kind of less expensive, easier ways to get it done. You've got Google with Project Loon doing balloons, and Facebook's got its own solar drones. They've invested in a company called Titan Aerospace. So I think there's just better ways to do it.
Well, what are the odds? An Apple Valley man was in his yard when a weather balloon dropped from the sky. And now Fox 9 has helped him figure out where it came from. Leah Bino joins me now. Leah, this is a pretty cool mystery for this guy.
Yes, but once we found the serial number on it, it was pretty easy to trace where it came from. The National Weather Service in Chanhassen. This is one of more than 1,000 locations routinely launching weather balloons around the world. Still, as our own Ian Leonard says, the likelihood of nearly getting hit by one, someone has a better chance of getting hit by lightning.
All of a sudden I heard a big thump right behind me, and I turned around, and this was laying in the yard.
Brandon Wilson had no idea what he was looking at after it dropped in his Apple Valley backyard yesterday, just 4 feet behind him.
I was just in shock, I felt the ground shake. It's not very heavy, but it came crashing down, that's for sure.
Now he realizes it's a weather balloon like this one, which based on the serial number we traced back to the National Weather Service office in Chanhassen. But they have been known to travel much further.
Here we go.
Going up about 1,000 feet per minute, weather balloons like this one, equipped with GPS and radiosondes, are launched twice a day. It goes up for about 90 minutes, measuring pressure, temperature, humidity, and wind speeds along the way.
That little instrumentation is called a radiosonde. That little weird-looking box of styrofoam is truly the building block of every single forecast that is made anywhere in the world every single day. It's called a radiosonde. That little weird-looking box of styrofoam is truly the building block of every single forecast that is made anywhere in the world every single day.
There are people working on satellite interpretation to do it. They're fairly good, but apparently they're not good enough yet to get rid of the balloons. So.
At about 20 miles up into the atmosphere, the balloon eventually pops, and a parachute is supposed to help the equipment drift back to the ground where people like Wilson might find them.
Crazy. It's not every day something happens like that.
No, it is not. As instructed by the paperwork attached to the weather balloon, Wilson plans to send it back to Kansas City, where it can be refurbished for another flight. Back to you guys.
Very cool.
Right?
Cool. I mean, really.
Think about it. Around 200 go up every day across the nation. And the
no
odds of that coming down and almost hitting somebody, they're astronomical.
Crazy. I was kind of hoping that it would have come from a more exotic locale, personally.
But this one was launched in Hawaii or something.
Yeah.
Not really. They go so fast.
Yeah.
Rise to about 100,000 feet. The balloon expands, fails, and they come straight down.
Unbelievable.
The future of space tourism is when, for most people, it's a lifestyle decision to go to the edge of space and see the world that they live in. I think it would be a tremendous shame to live my entire life on a planet I've never really seen. I think that sort of changes how you view life and really gives you a better appreciation.
We're working to make space as accessible as a commercial airline flight. We have people from all around the world who bought tickets to fly in the Worldview capsule. Our tickets right now are $75,000 a seat. The oldest person is in their 80s, so it's truly an accessible and exciting trip for people.
Air Force balloonist Captain Joseph Kittinger, Jr. is laced into an elaborate pressure suit in preparation for a daring ascent into the stratosphere.
The idea for balloons in manned space goes all the way back to Kittinger in the 50s. Before the age of rockets and the great space race, we were using high-altitude balloons to take people to the edge of space. And so it's this really old idea that's laid dormant really for the last 60 years, and it seemed it was time to bring it back. As we began to develop that project, the StratX program came along. The team really gelled around taking Alan Eustace to the edge of space and having him jump from the edge of space down very quickly. The team and that technology essentially formed the basis of worldview.
The balloon that takes the capsule up is about the size of a football stadium. So imagine looking out the window when it's completely dark out and there's an incredible starscape outside, like really nobody has seen except the astronauts. And you'll see the sun start lighting up the planet below you. You'll see the curvature of the Earth, but the sky will still be black. It's going to be the most extraordinary sight.
When it's time to come back, we open up a big parafoil that is about 3,200 square feet, the largest parafoil that's ever been operated. This parafoil, for example, is about 1,200 square feet, so it'd be about 3 times bigger than this one. The balloon itself falls essentially in a big ball of plastic towards the Earth, but then a team goes out and collects the balloon, and it gets turned into plastic bottles.
We really feel that taking people up in this way is going to really open the door to a space experience in a way that you really can't do any other way. Humans have always explored. We've always gone beyond. We always have. And we always must. That's what, in large measure, makes us human.
which is, quote, a balloon satellite, which, by the way, there's no such thing.
And that dude who jumped out of a perfectly good balloon, what's his name? Felix Baumgartner. He would have been about 2 millimeters above the surface of this globe. That's his edge of space jump. Now, you know, I don't, it's fine. He wants to, I don't have a problem if he does it, but the honesty of it would greatly diminish what I think people thought he was actually doing. And not only that, they made sure to photograph him standing there with a really wide-angle lens, which curves horizontal lines. So in the photo, you see this curvature of Earth's surface, and he said, wow, he's in space. Look at that. No, he's not. At that height, you don't see the curvature of the Earth if you are 2 millimeters above this beach ball. You just don't. That stuff is flat. That stuff is flat. That stuff is flat.
Not only that, you know, as they say, you know, as the area of our knowledge grows, so too does the perimeter of our ignorance. Mm-hmm. So